Thank you very much for this opportunity. I'm very glad to be here to talk to you about how epidemiology can help shed some light on 1.4 dioxane and some of the challenges and opportunities with conducting epidemiologic studies and exposure assessment with this particular chemical. So as many speakers today have already highlighted, there's been growing concern about 1,4-dioxane due to its widespread use, its presence in groundwater plumes, its emissions to the air from industry, and its classification as a possible human carcinogen. So for all these reasons, epidemiology has a lot to offer to try to fill some of the gaps and advance understanding of this chemical. Okay, so epidemiologic studies of any environmental chemical can be challenging, particularly when you're looking at chronic diseases or cancer, which is something I usually look at. This because we're often trying to estimate exposure over a long time period, sometimes decades, a lifetime, and there can be a lot of different things going on with the exposures. They could be varying by source, so you could have it in the water, the air, cosmetics, by location, where are you spending your time? The levels in the air and water can be changing over time. So trying to capture all of this appropriately is certainly challenging. And then we also have to think about factoring in for chronic diseases like cancer, some sort of latency period. So how long will it take for clinical health outcomes to manifest after the exposure? And I should point out, the exposure window could go back even to the in utero period, as there's growing research indicating that early life and in utero exposures may be quite important in terms of later health effects. So some of the challenges I've laid out here for 1,4-dioxane are that this idea that the critical exposure windows may cover long time periods, the exposure circumstances and pathways may be complex, and biological and environmental measurements that we often use can be difficult to obtain. And I'll be elaborating on some of the challenges with biomarkers throughout the talk. And there are some opportunities to obtain publicly available environmental monitoring data, such as from EPA, the National Air Toxics Assessment emission data, or monitoring data from the unregulated contaminant rule. But we have to really think carefully about whether these existing resources are going to have sufficient spatial and temporal resolution to be able to, again, appropriately assign exposures in a health study. Okay, so I wanted to kind of review some of the epi that has been done for this chemical, and it's quite sparse. There are 4 studies that I'm aware of that I'll describe briefly here, and 3 of them are occupational studies. So the first one is a workplace study in a chemical plant in Texas of 165 workers. The exposure assessment was assigned by experts who gathered information about job titles and tasks, and combined that with information from monitoring data that was available for that workplace. And they compared the overall deaths, and specifically cancer-related deaths, in their population, and found that the observed deaths were no different than what would have been just expected. So here you can see some of the numbers I've listed. The numbers of deaths and the numbers of participants in this study are quite small. something to keep in mind with this study. The second study was in 2 textile plants in Michigan. It was a matched design where there were exposed and control workers from these 2 plants. And one of the plants heavily used 1,1,1-trichloroethane as a cleaning solvent. And it was determined that 4% of the composition of this solvent was dioxane. So again, this study is not directly ascertaining dioxane, but dioxane was used as a stabilizer in this commonly applied solvent. So in this study, it was null as well. There were no health outcomes, and they were particularly looking at cardiovascular and hepatic outcomes that were associated with exposure to the 1,1,1 TCA solvent that contained dioxane. So the third study was also a workplace study. This one was published in German and reviewed in another paper. This one had 74 workers exposed to dioxane in the air, and they had some air measurements. And similar to the other 3 occupational studies, they did not observe any increased number of deaths or cancer-related deaths based on what would have just been expected normally due to background. So in these 3 studies, we can really draw very little conclusions from these because of their smaller sample size and other challenges in the exposure assessment, like not actually measuring dioxane, for example. So there has been one environmental epi study that I'm aware of that was just published last year as part of the SISTERS study. People may be familiar with that. This one was a pretty large study, enrolled 731 women, and they were assigned exposure to dioxane based on the EPA's air toxic assessment program, where they have census level estimates for dioxane exposure. And they also had blood samples for this population and were able to measure telomere length. Telomeres cap the ends of DNA and are protective, so longer is better, and shorter telomere lengths are predictive of various chronic diseases, including cancer. And they've identified an association between dioxane concentrations in the air in the communities and shorter telomere length. So taken together, these studies, again, are very sparse. Their most recent study, the environmental study, I think really underscores the need for additional research into this area. Okay, so as we're moving forward with our project that Vasilis had indicated earlier, we're planning to do some of this health work. We've been thinking a lot about how to best approach exposure assessment in the context of epidemiologic studies. And we have tools available to assess occupational exposures. Well-established tools like getting job titles, tasks, monitoring data. I apologize if anyone hears my cat, of course, is meowing right now as I'm giving my presentation. So I do apologize if there's background noise. With this exposure assessment challenges and options, we can use traditional workplace tools to assess exposure, like job exposure matrices, and anchor information about job titles with monitoring data. Like the EPI study I just described, there's the availability of air monitoring data to try to estimate that route of exposure. We really think groundwater, ingestion of contaminated groundwater is the dominant exposure route. And so the UCMR may be available to inform some of this. We could collect new samples, environmental samples, water samples, air samples, and we can also do biological monitoring. Biomonitoring does raise some issues of temporal variability, specificity, and sensitivity, which I will get into now. Okay, so for biomonitoring of dioxane, there have been some studies investigating this, conducting biomonitoring. Dioxane is rapidly metabolized to HEAA as its main metabolite. One issue with using this in a health study is that it is not a specific biomarker, so it's not specific to 1,4-dioxane. It's also a metabolite of other contaminants like ethylene glycols and glycol ethers. So that is a concern that if we did measure this, we wouldn't be able to tie it specifically back to 1,4-dioxane exposure. On the right-hand panel, this indicates also another challenge, this rapid excretion of dioxane, which means that any urinary measurements would really be indicating recent exposure, which is not necessarily optimal for a study of cancer or chronic diseases, or it could require repeated measures, or if we think the exposure is relatively constant, we may be able to overcome this as a challenge, but it is something to consider. Okay, and here's a slide summarizing the existing biomonitoring studies. So several have used urine, and a few have used blood. So I wanted to move on to some of the challenges with using whole blood and measurements in blood as another biomonitoring tool. So this, if I could draw your attention to the fourth box here, this was an Hines study, a nationally representative sample of the adult population conducted by CDC. They developed a rather sensitive method to quantify dioxane in human blood. But as you can see here, in the over 3,000 people sampled, they did not detect any 1,4-dioxane. So this low abundance of 1,4-dioxane in biological specimens is a significant challenge for exposure assessment. That brings me to some of our new work that we have developed, and I should say this work has been done by Crystal Pollitt. Dr. Pollitt is another professor in our department, Environmental Health Sciences, and has been spearheading this effort in developing biomarkers for 1,4-dioxane, and I appreciate her helping prepare these slides. So this slide indicates the sample analytical workflow for detecting 1,4-dioxane. We can't just measure it in blood or water or urine. There has to be some sort of sample preparation to really concentrate the sample. And so here we've listed a variety of different sample preparation techniques listed as with increasing sensitivity. And we have opted for this solid phase micro extraction to really try to enhance sensitivity of our methodology. And then because of the low molecular weight, we're using gas chromatography for separation of the compounds. And we have a variety of instrumentations and tools available for detection. And again, we've opted for this mass spec with the selected ion monitoring mode to really enhance our resolution and ability to detect these compounds at low abundance. So this is enabling us to do really targeted measurement and analysis of this particular chemical. Okay, and this slide is really just designed to kind of illustrate, I got some animation here, the simplicity of the method. The blood samples can be spiked and then put on an auto sampler, and then the samples can be run. It's actually pretty low in terms of personnel requirements, and you know, a fairly low intensive type of method, unlike some other procedures. So that's kind of nice. Okay. So here I'm presenting some results from Dr. Pollitt's lab. In panel A, this is an example of the chromatogram and the results that we get from her methodology by using this micro extraction and then the GC Orbitrap instrumentation. We are able to detect 1,4-dioxane, as you can see here. It comes out at 88, the molecular weight of 88. This is one of the participants in a pilot study. So you can see a nice clean peak here for 1,4-dioxane. You know, in other methods that are still quite sensitive, some of these peaks, these neighboring peaks, would be kind of consumed in the dioxane peak and be difficult to really get that separation. So once she developed this methodology, we wanted to apply it in a pilot study. So we were able to obtain whole blood samples from 4 residents of New England who had no known or obvious source of exposure to dioxane. And this panel C is showing the results of the analysis from those 4 participants. And what we really wanted to point out here is that this dashed line, the 1,500 picograms per milliliter, was the limit of quantification by the CDC's method in NHANES. And you can see that our pilot participants are at about 1/3 of that concentration, so indicating really the need for very high sensitivity and high resolution methods to really, if we want to really detect this chemical in the general population. It may look a bit like there's not a lot of variation in the concentrations, but because of this scale, I think it's kind of masking some of the variability. You know, we have concentrations in the blood ranging from about 500 to 700, and again, in a very low exposure group. And through this method, we were also able to quantify the co-contaminants that typically occur with dioxane. Okay, so we're really excited about this method that seems to be able to detect low levels. I should point out, though, there are still some challenges. This blood method and the blood biomarker still likely, you know, represents only recent exposure. I think we need a little more work to understand the exact pharmacokinetics of the elimination, but dioxane is rapidly eliminated and it doesn't bioaccumulate. So we'd have to do some work to confirm that people's exposures are fairly consistent, you know, in order to use this as you know, a marker of longer term exposure, but it's at least a good measure of recent exposure, and it's specific to 1,4-dioxane. And I think there's high probability that it could also be a good surrogate for usual exposure in populations with contaminated drinking water, certainly. Because of its physicochemical properties, you cannot store these blood samples and freeze and thaw them and then measure 1,4-dioxane. So this is another challenge for epidemiologists. This could not be used in a retrospective study where you have banked blood samples, because you will have too much sample loss through the freeze-thaw process. So we are planning a new exposure and health study that will require kind of prospectively collected biospecimens. We're planning to do this work on Long Island, where there have already been documented hotspots of dioxane in the drinking water there, as shown in this map here. And we will be measuring the blood samples kind of in real time on a rolling basis. The CDC recommends that the samples get measured within 6 weeks. So that is, again, another consideration for epidemiologists. But I will close with that. We are really looking forward to continuing this work and bringing this to some population-based studies, and we think that the epidemiology would be really critical to informing human exposure, other research, and some of these state and federal guidances. Thank you.
So hello to everybody. I know I'm the last speaker, so I'm going to be very quick for you. My presentation is simply on 1,4-dioxane and getting it banned from common household products. This wasn't a big topic today, so this will be at least a little bit different than the previous terrific topics. So first slide. Just so everyone knows, and I'm sure many do on this call, and this is relevant for this topic here, Long Island is a designated sole source aquifer, which means 100% of the drinking water comes from underground. We have 3 layers: epiglacial, that's where most of the private wells are; the Magathy, that's where most of the municipal wells are; and then we have a very deep layer called the Lloyd, where we do have some municipalities that drink from the Lloyd. But we do not have another source currently of drinking water. So everything we do on the surface seeps down through this through these aquifers and through the 3 layers. Vasilis, next slide.
I'm sorry.
Okay. So the first thing we did was we took all of the EPA's data and we put it into an interactive map. And to the best of our knowledge, this was the first interactive map created for 1,4-dioxane. It's still the only one for Long Island. And we made it so that a homeowner can click on the little icon you see there and understand what the EPA data said. So obviously the green one means that it was below the 0.35 ppb. The red is above it. So there was a lot of data sets. We have a lot of different drinking water suppliers here on Long Island, especially in Nassau County. After we published the map, it went viral. It got 40,000 views in the first day that we published it. So Long Islanders have a history of wanting to know what's in their drinking water, and they also are very concerned about what's in their drinking water. So the map then, I just want to bring your attention to, there are some spots here that we knew the 1,4-dioxane was coming from legacy contamination, right? Legacy industry. But then there were data sets and data points across this map. Like if you look at Montauk, for those of you who don't know, it's the very tip of the South Fork. We call it the end. They don't have industry in Montauk, and they pride themselves on that, as they should. But yet there were wells with 1 or 2 parts per billion, or 0.6 we found. There was 0.7 in areas that did not have industry. So we were wondering, where could it come from? If there's no industry, there's no real, kind of legacy contamination we could find, leaking storage tanks, nothing like that was around. What could be the source of these very small hits and very small detections? We don't need that. You guys have already heard enough about that. Keep going.
Okay.
There we go. So we started to research, and many of you know that 1,4-dioxane is also in products. There's been, before we got involved, very, very limited testing on how much 1,4-dioxane is actually in products. When I say products, I mean personal care products, your shampoos, your laundry soaps, your bath gel, baby bath products, you name it. So you also probably know that 1,4-dioxane is not an ingredient. That's why we call it the hidden carcinogen. It is a byproduct of the manufacturing process. So if the homeowner goes to the store and looks at their product, you don't see 1,4-dioxane listed on the ingredient label because in fact, it's not an ingredient. So you don't know it's there. So we started out in 2018, we said, okay, well, could it be that it's coming from products? Because on Long Island, we have some large sewage treatment plants, but we also have very small, what's called package plants, and they discharge into groundwater. We also have, which is actually mind-blowing, about 400,000 septic and cesspool systems in Suffolk County, and about another 30 to 40,000 septic and cesspool systems in Nassau County. So obviously anything that's washing down the drain is leaching out into the groundwater system through the septic systems, but also through many of the package plants, the STP package plants that are discharging to groundwater. So in 2018, we tested 30 products. We just tested 30. We got a grant from a foundation, and we found that out of the 30 products tested, 23 of them contained 1,4-dioxane. We weren't really sure what to expect, but we thought that was pretty darn high. We then started to get, which was kind of fun for us, all of these calls from our members saying, didn't you test my product? What about this product? What about this shampoo? I use this on my baby. And people kept calling the office, asking us to test products that they've been using. So we received another grant. We increased the amount of testing. We used a New York State certified lab that had a very low detection limit. And in 2019, we went back again and tested another 50 products for now a total of 80 products. We did some research. We looked to see what is the most popular laundry detergent in America. And for those of you on the edge of your seat, I can tell you it's Tide. So we looked to see what are the most common products in these categories and what do they have. So we tested a wide variety of products. We have named these 12 the Dirty Dozen because they earned that name. Victoria's Secret, which we actually weren't even going to test, but we decided to do that at the last minute because we know a lot of teenage girls use these products. And we like to say, we now know Victoria's Secret. She's poisoning us, but people get nervous that I'm going to get sued, but we have, insurance for that because we're a nonprofit. But anyway, Victoria's Secret, there's 17,000 parts per billion in their Bombshell body wash, and in their Love body wash, there's 16,000 parts per billion. Tide, all of that Tide going down the sink, 14,000 parts per billion. And as I read these numbers, let's remember this goes right into the groundwater. And now our drinking water standard is 1. Ivory, which is marketed as being pure and natural and so wonderful, 11,000 parts per billion. Dreft, which we tested specifically because one of my coworkers, the pediatrician, recommends Dreft as a laundry soap when you have a newborn, 10,000 parts per billion. And we can go on and on. Baby Magic, that we put babies in to give them a bath, 7,600. And I understand, just so you know, that, there's two things, right? There's drinking water exposure and there's also dermal exposure. We looked far and wide for studies on dermal exposure, and there's not too much out there. There's the European study, which is used as an advisory document to say that your dermal exposure should be limited to 10,000 parts per billion. but there aren't any studies on compilations of exposures. So if you're, taking a bath with Victoria's Secret, and then you're washing your hair with Pantene, and then you're washing your dishes with the dish soap that has 7,700, those three products alone, which you could be exposed to most likely the same day, now you're over, 25,000 parts per billion. Next slide. So then, just to give you some good news, we wanted to see if the all natural products really lived up to their label. I'm happy to say they did, actually. Aveeno, which is not really marketed as all natural. I mean, it's marketed as, somewhere in between. Anyway, both of their products, their baby product as well as their shampoo, came out with non-detect. Baby Organics, which is organic. Burt Bees, one of my personal favorites. Not that you want to know that. For some reason, Dove came out with non-detect. Seventh Generation non-detect. And actually, I spoke directly with a representative from Seventh Generation. He said that they used to have small detects of 1,4-dioxane. And when they tested their own product and they realized that, they actually took a year to a year and a half to reformulate it. So it did not have any more detections of 1,4-dioxane. So they get a little bit of a gold star. Next. I don't know why my staff put this in there. They think they're very funny. So from this shopper's guide that we produced, it actually created a very big stir within the public. The public wants to know why they're bathing and washing their hands and washing dishes and bathing their children in this highly toxic chemical. And so we worked with, in New York, our state Senate and Assembly, particularly the chair of the state Senate Environment Committee, Senator Todd Kaminsky, and the chair of the Assembly Environment Committee, Assemblyman Engelbright, to pass legislation that bans 1,4-dioxane in products in New York. It was I will just tell you, a very fierce battle. And I will be very honest, there was lots of corporate industry, we like to say, on the playing field, which means in the halls of Albany, Procter & Gamble, Lysol, Dow Chemical, you name it, that was saying the bill should not be passed because they will have to take those products off the market. But I feel that since Seventh Generation found a way to reformulate their product, and they've done so successfully, and their sales have increased, not decreased, that other industry could also do that, because now that we know the high levels in these products, we should do better. And also, now that we knew New York was moving towards a drinking water standard, we don't want to keep contaminating our drinking water through products at the same time paying to filter this chemical out of the drinking water. That doesn't make any sense. Next slide. So actually, you probably don't need this because we've just heard enough today. There we go. Next one.
Oops, what happened?
I don't know. You put me back at the beginning. You want to hear it all again?
No. For some reason, it just
That's okay.
hit me.
I think the bottom line here is,
Oh,
okay,
you
there we
see?
go. Great. So the bottom line here is that the law has passed. It was really legislation, frankly, that was driven by public demand. I've been doing this work for 30 years, plus a little extra. And I've never really seen I've seen it before, but it's rare. So much public engagement, so much public enthusiasm for state legislation. And the public actually made their voices known. They were informed. They were passionate about this bill. And we're looking forward to it going into effect in 2022. So it was a big success. It was a lot of work, but it came together nicely. Thank you.
Thank you very much. And as a matter of fact, it's one of the highlights. New York is the first state that banned 1.4 dioxane from the households. The bill was, as Adrienne said, was very recently signed, and it's going to take into effect. And I think that was a very big achievement. And this is how, you know, research and community engagement that can lead to policies. So with that, we concluded. I want to thank all of you, but don't leave yet, just yet, because Ron Hines is about to pick up and start some discussions. And you know, feel free now that we can have a discussion. Ron, I'm going to pass the podium to you so you can moderate this discussion.
Thank you, Vasilis. Very good presentation today. It was very informative. I don't know a lot about 1,4-dioxane, but I learned a lot today. I've been trying to monitor the questions as they've come up on the chat. I have put some down myself and trying to look. Some of them were answered as we went through the day. I'm going to throw out one question, though I think that was sort of a bit controversial, and I would ask individuals to speak up on this. Hopefully we won't have everybody speaking at once, which is always a danger with these platforms. But I think this was Gary mentioned in his talk earlier this morning that they're using a linear low dose type extrapolation to develop some of the MCLs for 1,4-dioxane. And the question was raised by Hunter as to whether or not we should be using a point of departure type approach. And so I would like to have individuals, some of the speakers, perhaps comment on what is the most appropriate approach. Should we be using a point of departure? Or should we be using a linear extrapolation to a low dose for determining the risk? Any comments on that? Gary?
Yeah, Ron, since you called out my name to start, I'll kick it off and can further talk about our basis. And that is essentially following EPA guidance and consistent with all the other determinations we've made for drinking water in New York State historically. And that is that when you don't have a confirmed mechanism of action that would show a threshold below which, you know, either the slope of the relationship would be very different than in the observed range. So when you don't have that kind of biphasic, non-monotonic, a mechanism that clearly points out that that's what you would get, and where it is, you know, plausible to have a monotonic slope when you don't know the mechanism, which we don't for 1,4-dioxane, and whereas there's a lot of research going on right now as to what that mechanism is. Maybe in 5 years or some amount of time going down the road, we'll know better how to extrapolate to low dose. So the default, according to the EPA cancer guidelines, is the linear default. And you know, obviously in IRIS, you know, they point to that when they derive the 0.35 as the associated drinking water level that would be associated with their with the slope factor that they calculated. And EPA normally does calculate a slope factor for those situations where they either have a linear mechanism or where they don't know the mechanism as the default approach, and that's what's on IRIS. So we're basically, you know, using IRIS from 2011 and that slope factor that was calculated by EPA.
Ron, this
Yes,
is
Linda,
Linda.
go ahead. Go ahead, Linda.
So I think we have to remember that in about 1986, Kenny Crump showed that because you had additivity to background cases, and certainly when you're dealing with liver tumors in mice, you're dealing with additivity to background, low dose linear is the appropriate thing to use. The other thing is on a population level, thresholds don't really exist. And I would remind everyone, at least in my opinion, thresholds are often determined by your analytical methodology. and what your assays are. And as you get to different assays, you start getting to lower and lower kind of doses. So in my mind, I think using the low dose linear approach here is very appropriate.
I'm not sure if Hunter is still on because I think he's the one that raised that point. Hunter, you still on? Doesn't sound like it. Yeah, I was playing devil's advocate.
Sorry, Ron, I'm here.
Okay.
Yeah, I guess my response is, is everyone in this country smarter than every Canadian? I mean, there's clearly another side of this camp, and I'm not the voice for that camp because I'm not a toxicologist, I'm a soil chemist. And so I clearly am not educated enough to say, but, rather than just talking theoretically, what exactly about what the Canadians have published on this matter is wrong? And what is it not, justified?
We can't speak for the Canadian thought process on this particular chemical. And we've looked at, as part of the Drinking Water Quality Council process in New York State, what they wrote up. It came in right around the time that we were briefing the council, so we made sure they saw that. And we know that folks in Michigan were looking at various ways before us. The folks in Michigan were looking at various ways to evaluate it as well. So it's been looked at closely, and the evidence for a point of departure, nonlinear mechanism is kind of sketchy and does not, uniformly line up. Let's put it that way, without going into a lot of the weeds on it. But it just doesn't line up as a strong line of argument with the kinds of evidence that we've seen EPA use for other chemicals that are more a point of departure approach. So, why Canada is where they are, you can ask them that. But we've seen their documentation, and it certainly doesn't remove the fact that they don't know what the mechanism is either. The default here is if you don't know, you take the reasonably conservative approach.
And I think Linda's point is a strong one too, that in a population, because of variability in the population,
Exactly.
and also susceptible groups within the population,
Exactly.
the linear low dose extrapolation is probably an appropriate one at the current time for risk assessment. Speaking of mechanisms of action, I'd like to hear a little bit more from Vasilis or others in his group. This whole idea of what's causing these alterations in gene expression. If you look at the panel of genes that are being altered, it was brought up as to whether or not there might be an epigenetic effect. And you sort of mentioned in the chat that you're going to be looking at that, but do you have any idea, or do you have any leads as to that are pointing you in a specific direction of what epigenetic mechanisms you might be looking at?
We don't have anything, and I have also, Yin can also chip in here. We're going to get a young Jew from my department involved on that. We have thought about, we have all the samples ready for epigenetic analysis. We don't have an idea, but it's, nobody has looked at epigenetic changes. And Jason, thank you so much for bringing it up. We have already been contacting to do that. And Young, is Young still with us? Maybe he left. Oh no, he's here. Young. We are going to look. So we don't have an idea what is the changes. However, what this series of experiments will tell us is what is the mechanism by the NK1 is induce and stay up. It's definitely, it's not NERV2, is not AH receptor. Is it epigenetic? Could be. Is it through another pathway? It could be. And as I was saying, I had a meeting with David Ross from School of Pharmacy, University of Colorado, and he says also they have seen something. They have a paper that they're getting ready. They have seen also the NK1 being regulated completely different and in opposite way from the other NERV2 genes on another system. I cannot reveal the information because this was, unpublished data. But the answer is we don't know. I mean, most likely it could be epigenetic changes, but we don't know. We have to find out.
So you're planning to look at just DNA methylation or perhaps histone modifications or microRNAs or?
Well, we're going to start with the methylation first, and then we're going to move forward, you know, to the other. The microRNAs are also a big case as well.
I can add a point.
Yin, yeah, can you speak up a little bit more?
Can you hear me?
No, not very well.
Can you hear me better?
A little bit.
Yeah, very faint.
Oh.
Very faint. Come closer to the microphone.
Okay. So one of the Western blot that
There you go.
showed, we measure the level of the, which is normally used as a DNA damage marker, is the phosphorylation of histone 2 variant. Actually, we just finished the data last week. It looks like the histone, this variant, which is very sensitive to DNA damage, this histone, not the phosphorylation form, just the parental form, is kind of very sensitive to dioxane treatment. It's reduced at the parental level, but the phosphorylated form increased. We need to confirm a little bit more on that set, but it looks like there are very likely epigenetic molecules that are involved in cellular response to dioxin.
Sounds very promising. Like to perhaps turn to another topic. Dave Adamson pointed out some of the issues that we're having with our methodological approaches to measuring 1,4-dioxane and some of the concerns that those raise. And yet Nicole presented a method that looks very promising, though there are still some limitations to it. And we're curious to get Dave's input on what he thinks of some of the approaches that Nicole presented.
Yeah, I thought her talk touched on some really interesting issues, and I think part of the struggle that, you know, I'm a consultant and we work with a lot of, you know, projects and clients where people are trying to do things quickly and cheaply, and getting new things in place is hard and takes a lot of work, and getting commercial labs to do that and the methods standardized and all of that. That it's hard to make those sorts of advances. And so I'm glad that there are people that are out there that are essentially you know, pushing the boundaries on this and getting better methods. Detlef Lab, you know, they can get as low as we need to get on these things as well. But we need to make a push to sort of, I'm not saying that the commercial labs are letting us down or that the people that are promulgating methods are letting us down, but as somebody else said, we can do better and we should do better. So I'm always encouraged when I see people producing high data quality.
And we're also on the environmental side working on a method that's basically ready, where we are taking advantage of tandem mass spectrometry to resolve interferences with VOCs. So we can basically now combine methods 524.3 with method 4,1,4-dioxane and other ethers and be super sensitive with it. So it's going to come out, and I think in the end it'll actually be a simplification over what we're doing now.
I'm going to push that just a little bit further if I could. Early on in the presentations today, you know, it was mentioned that the reason why 1,4-dioxane has become a concern is because we started looking for it, and I know very well that same issue occurred with the PFAS. We thought we'd sort of conquered the problem when PFOA and PFOS were banned in the U.S. And then it turns out there's some 1,000 different PFAS that are out there in the commercial market, probably 3,000 to 5,000 total PFAS that exist, and in different registries. And it's because we started to look for them. has anybody thought about doing a more non-targeted approach to start looking at these environmental compounds, and perhaps whether that would also pick up some of the chlorinated compounds that are co-occurring with the 1,4-dioxane in a more objective way to look at these samples? Linda, you were shaking your head. Do you have any comment on that one?
I shouldn't be visible. I mean, I guess, Ron, when you said that we're seeing it because now we're doing more testing, it reminded me of someone else in our country has saying we're having more COVID cases because we're doing more testing. And I'm sorry.
I didn't mean that in a bad way, Linda.
I know you didn't. I'm sorry. But I'm sure Detlef can possibly respond a little, the whole issue with PFAS right now. There are about 4 methodologies that are being used to do total organic fluoride analysis that people are starting to do. And when you do that, you find that we're really only defining maybe in many cases, at least in water, 20-25% of what's out there. And the data for blood is much more even limited. So I think some kind of untargeted testing, whatever you're looking for, is something worth talking about.
Well, let me add a little bit on that before Detlef goes on. Untargeted and targeted. I wish I could show you. We have done an analysis of about 2,500 chemicals in the blood, just exogenous. This is on Young's project for asthmatic children in various areas, and we are detecting various chemicals. So the point here is, can we develop big libraries that we can do? We can use them as running at one high throughput screening, either environmental exposures or even the blood, to try to characterize the exposome. And this is what we're doing, and I would like to discuss this further with Detlef as a part of larger collaboration. Right now, we have a capability. My lab and my collaborators have also, we can do about 3,000 various chemicals. I'm not talking just only PFAS. I'm talking pesticides, PCBs in a single run, and we can get this data. And this coming back also in terms of 1.4 dioxane. Yes, it's fast metabolized. It's very difficult to identify it. So this is what we're doing metabolomics in these studies. And I don't know if Georgia is on the run. This is why we're trying to compare both liver and plasma on all these studies that Ian is doing right now with low glutathione, low and high glutathione, normal glutathione, try to identify processes, not single biomarker, processes that you can use to characterize exposures, that you can use some of those in blood or urine of humans to characterize the exposome, the exposure of these chemicals to humans. Detlef, do you want to say something? You had to add something.
Well, and I think when we think about non-targeted analysis or untargeted analysis right now, that's a huge focus in the PFAS world and in the LC mass spec world more broadly. But on the GCMS side, it's maybe slightly less common right now. And I think a lot of method development is still needed there because based on, we don't have a high-res instrument in my lab, but from what I hear from people who are beginning to work with this is that, some of the libraries that we use, like the NIST spectral libraries, they need to really be revisited when it comes to working with the high-res instruments. So it's not a simple plug and play, but it'll require some serious method development.
Yes, for GC, I agree. For LC, things are a little bit better though. Yep. For GC, yes, we do a lot of method. I wish is Georgia on the call?
Yes, I am.
Can you speak up a little bit on that?
We have done a lot of LC work on also dioxane that we gave to wild type mice, and we treated them for 1 week and 4 weeks. We saw minimal liver damage, but and we also did untargeted metabolomics, LC. And we saw a trend, but probably these mice should be given Dioxane for a longer period of time. Also, as far as the untargeted, the MS approaches, both LC and GC need work, and we have developed our own library to be able to detect these molecules. That's why we identify them based on our own metabolites, and we were also able to develop an LC method to detect not only the parent metabolite, HEAA, but also the dioxane on our triple quadrupole. And because of the nature of the triple quadrupole, we were also able to have a great sensitivity and go very low and be able to detect in very low concentrations dioxane. But for sure, we're working very hard on developing all these omics and multi-omics data, because we also did an integrated multi-omics approach. We integrated our LC and targeted data with the RNA-seq data that we did on the livers, and we were able to see the processes that changed, as Vasilis mentioned, along with the genes that they were that changed. And we're going to do the same with the mice that Yin is working on, with the GCLM knockout mice, and we are seeing really great results. But the take-home message from these studies was that these mice need to be treated for a long time. So it's a long-term exposure. It's not acute. So even if you treat these mice like for a really high dose for like 1 month, you won't see many changes. These mice have to be treated for like 6 months, a year. And I think that also replicates, that simulates the what happens in real life. The dioxane is a long exposure, and the causes chronic problems and problems after people are being exposed for a very long time. And that's, I think, also it's the difficulty to be able to detect the changes that are caused by dioxane.
So let me ask a completely different question, and something I didn't hear anything about today, and yet is a little bit near and dear to my heart, at least, and that is developmental toxicity. Has anybody looked at developmental toxicity of 1,4-dioxane?
I don't think so. That's a good question, though. That is a very good question.
You know, and particularly we talked about, you know, its rapid metabolism, for example, and suspected that CYP2E1 is involved, and yet we know from some of the studies I did involved in early on, Gail McCarver was the lead on this one, that CYP2E1 actually is not very well expressed in the human liver. In fact, it isn't expressed until the 3rd trimester, and even then, at only about 5% of adult levels. And so one might expect that if 2E1 is critical for clearance and maybe detoxification, that you really don't see it, and it could be dangerous to the developing fetus. Linda?
Yeah, there was in the ATSDR review, they talk about a developmental rat study saying that it may have been fetotoxic. That's all I have quickly at the moment.
Yeah, might be worthwhile pursuing. Yeah, Gary.
Yeah, in the EPA 2011 profile on iris, there was, I believe it was there. Yeah, there was a 3-fold uncertainty factor given as an additional to the RFD based upon liver for the lack of sufficient reprotox data. I think they're missing a 2-gen in one species. So yeah, there's gaps there.
Yeah, sounds like an area that should be pursued.
Yeah, and I think Zayan is our cohort, birth cohort. And is Yahweh still there? Yahweh and Zayan are still on call?
Yes, I'm here. Oh, no. Yeah.
No, I'm talking Yahweh is Yahweh, not Yahweh Day. I'm talking about birth cohorts. Please, I cannot hear.
I know
anyway.
Gloria just posted something to the chat on a developmental tox study. It was I have summarized in the iris.
Summarized by iris, yeah.
Yeah, but evidently, again, probably very limited knowledge on developmental toxin in an area we're probably worth pursuing. Bacillus, I'm not sure if anybody else has any questions that they would like to bring up.
I have a question to bring up. Why do we have snow and you guys have sunny skies and
Should have been here yesterday. It was all rain here yesterday. So.
And it's chilly. We finally have fall.
Yes. You see me, I have a vest on. Yesterday I was wearing a short sleeve shirt.
Well,
I'm
I
outside.
have the heat on.
I
saw that.
Yeah, I'm outside on a screened-in porch. So.
Yeah, me too. But the temperature is colder now than it was this morning.
Yes.
Temperature's dropping.
Yeah.
Well,
no complaints.
Before you close, Ron, I want to thank all the speakers, all the audience, the questions, everything. And I'm going to follow up with all of the speakers regarding this special issue that we can send. And also I would like to invite, people that they might be interested. We're going to create, I hope we have all the emails from the people that they have participated, and we can keep that email list and we can share the information. Detlef, I will be in touch with you along with Hunter and also Dave. I will be in touch with you guys, especially as we forming the final stages of our P42 application. And I'm looking forward probably to collaborating with you very closely on that.
Sounds good.
Before you close,
yes.
Could you please share the link to this video and also all the notes?
Yes, I was gonna say yes. I will. We have recorded the conference, and with consent of all the speakers, we can release it. And it will be a separate email asking for your consent. Everything has been recorded. And we also asked the speakers if you could provide me all your slides so we can make it as a PDF available for everybody. And Yin, we're willing also to share our unpublished data with the promise that they will be treated as a confidential. But we have no problem to share that. Okay.
Thank you.
Well, thank you all again. We also want to I want to thank Damaris. Is Damaris still on the call? Sally, thank you so much. Thank you, everybody. I really appreciate all your talks. I learned a lot today.